So yeah, good morning everyone. First, thanks Pete for that nice introduction. It's really nice to be back here at BQIT this year. This year is the warm-up speaker for all the great talks I'm going to have later today. So today I indeed want to talk about something which I'm going to call general purpose quantum algorithms. So these are algorithms firstly that you run in your general purpose quantum computer that hopefully people here at Bristol or elsewhere have built for you. And as well as being algorithms for a general purpose quantum computer, they're going to be general purpose algorithms themselves. So algorithms that you can use for many different tasks rather than being designed for one specific task. So everything I say is going to be really based around a couple of papers which are on the archive, or maybe you might say German versions as well. Okay, so let's get started. So roughly speaking, we can divide the quantum algorithms that we know, our algorithms for our general purpose quantum computers, into two types. We have some algorithms that achieve exponential or perhaps super polynomial speedups for some specialized problems. For example, simulation of quantum systems, which is very important, or integer factorization, Shor's algorithm breaking RSA, and also algorithms which achieve some kind of polynomial speedups. So, as in the quantum runtime might be the square root of the classical runtime or something like that, for some more general problems, like, for example, unstructured search via Grover's algorithm. So, you know, this I guess is perhaps not a very precise classification, but it's a good kind of intuition to have that we have these two kind of types of quantum algorithms in general. And I want to talk about the second kind of algorithms today, these kind of general purpose algorithms. And in particular, I want to tell you, assuming I have time, about two quantum algorithms for different but both very sort of general tasks. One is a quantum algorithm which can be used to solve constraint satisfaction problems more efficiently than we can do classically. And another is a quantum algorithm that can be used to speed up Monte Carlo methods, which are useful in a number of numerical type problems. Okay, so I just said on the previous slide that in general, when we have a general purpose quantum algorithm, this often doesn't give us an exponential speedup, it gives us some kind of polynomial speedup. And in particular, we often get a, perhaps, let's say, square root speedup over classical with these kinds of algorithms, like Grover's algorithm. So, you know, the quantum runtime might be the square root of the classical runtime. And a priori, it might not be so clear that this is interesting because you know, it's certainly a lot less dramatic than an exponential speedup. And we might imagine that building a quantum computer is very hard, and maybe it's not really worth doing it if all we're going to get is a runtime that's the root of what we would have classically. So in order to see whether this is interesting, it's probably worth doing some kind of back-of-the-envelope calculations. So just to, you know, put a kind of very sort of simple, you know, data point or two on the slide, we might imagine that we have some problem which is very hard to solve classically. So if we have an instance of size n, so we're given a problem and it's the input for this problem is n bits long, for example, or you know, we just kind of parameterize the input by some size n, and we might imagine that we only have an exponential time classical algorithm for this problem. So the best classical algorithm we have might run in time 2 to the n. So this is not totally unrealistic because if we have some kind of NP complete problem, for example, often the best algorithms that we have do run in time roughly 2 to the n. And we might imagine, say, if we have one of these quantum algorithms that gives us a square root speedup, that we have a quantum algorithm that can solve the instance of size n in time square root of 2 to the n. So it gives us a square root speedup over the classical algorithm. Okay. So, you know, this would be the case, for example, if we use Grover's algorithm for unstructured search and we apply it to some extremely difficult classical constraint satisfaction or optimization problem where the best algorithm we have, you know, is very naive and runs in time 2 to the n. So then let's work out how long it would take us to solve, you know, some sort of reasonable problem size for the classical computer and for the quantum computer. So imagine we've got a classical computer, which might be your laptop, that has a clock speed of 1 gigahertz, let's say. So what I mean is it can do one elementary operation in that's 1 nanosecond. And this is obviously slightly slower than the clock speed in your laptop, but you might imagine there's some overhead to do with the operating system or some other hardware-related things. And let's imagine that we have some kind of quantum computer that has a clock speed that's a bit slower of, let's say, a megahertz. And this number, at this point is, I guess, kind of made up because we don't have large-scale quantum computers. But I got this one from a paper from a few years ago about a superconducting qubit architecture, where they estimate that this is perhaps a reasonable speed of the clock speed of a quantum computer. In their model, making various assumptions and so forth. And, different architectures, you might get different numbers here. Maybe it would be a bit faster, maybe it would be, reasonably slower. But still, at least this is a number that has been written down in a paper as being not totally unrealistic. I mean, we would certainly expect this to be slower than the classical computer because, we need to have classical control electronics and so on, so probably we won't be able to outperform the classical clock speed, but we might expect it's not, ridiculously slow. Okay, so then let's look at an instance of this problem, our kind of made-up problem here, which is of size 70, so n is equal to 70. Then if you plug in these numbers here, the square root of 2 to the n and this clock speed here, you get that you can solve an instance of size 70 in a bit less than 10 hours, I think, so I've done the maths right. And on the other hand, if you tried using this algorithm classically, you'd need over 37,000 years. So your classical computer running this classical algorithm is dramatically slower. And I guess the point here is that this is a kind of useful runtime. It's under 10 hours here. But the over 37,000 years is not useful because you're not going to see it, see the answer in your lifetime. I mean, another way I could have put this is that the quantum computer has some kind of constant factor, I guess, speed up over the classical computer here, which I think is something like 10 million times. So you could say that you need 10 million classical computers of this speed in order to match what the quantum computer can do. Okay. So this, at least to me, suggests that it is worth thinking about these polynomial, square root type speedups, even though they may be more sensitive to the exact details of the quantum architecture than the more dramatic exponential speedups that we also know about. Okay. Right, so what I want to tell you about the rest of the talk is a couple of different approaches to achieve these kind of square root speedups. And the first one I want to talk about is a way of accelerating a classical approach called backtracking. So this is a very general approach for solving constraint satisfaction problems, or CSPs. So what's a CSP? It's specified by a sequence of constraints and some variables, and we want the constraints to all be satisfied by the variables. So we imagine we can assign different values to these variables x1 through xn, and some of the values we assign them will satisfy the constraints, and some of them will not satisfy the constraints. And we want to find a way of assigning values to variables that will satisfy all of the constraints, if such a thing is possible. And for many constraint satisfaction problems, the best classical algorithms that we know for this sort of task have exponential runtime in n. So they're very inefficient. A nice example of this, a very simple one, is colouring a graph. So in the three colouring problem, we're given a graph, as in a set of vertices and edges, like here, and we want to assign a colour to each vertex, picked from one of three colours, let's say blue, red and yellow, such that no adjacent vertices share the same colour. For example, here, we've assigned the vertices yellow, red and blue, and adjacent vertices are all have different colours. So this is a valid three colouring of the graph. And we want to, so in the three colouring problem, we want to find a valid three colouring, or say that there is no such three colouring. And this is an example of a constraint satisfaction problem, because the constraint is that a pair of adjacent vertices shouldn't share the same colour. So, right, one natural way that we might try and solve the three colouring problem is a kind of trial and error approach. So imagine we've got this graph up here that I showed on the previous slide, and we want to colour it in with red, yellow and blue. And to start, and we're going to take a sort of very naive approach and just try some things and see what works. Okay? So we might start out by picking this vertex in the bottom left and try assigning this one a colour. So we might try either red, or we might try yellow, or we might try blue. So we can think of these as exploring different possibilities. So we might choose red, we might choose yellow, we might choose blue. So we have 3 different possibilities to explore. Okay, and now next we might pick this vertex on the bottom right. And again we might try red or yellow or blue to assign to this vertex. We're just trying things and seeing what happens. But now we can see that if we choose red, then this is immediately a bad idea because there was a red vertex next to it. So we know that there's no point in carrying on with any other colouring of the other 2 vertices because these 2 are both already violating the constraint that they should be a different colour. So no way we can assign a colour to these vertices will be any good. So we shouldn't continue with any other colouring of those. But these ones, on the other hand, we don't know yet. We might be able to extend these to a full colouring of the other 2 vertices. Okay. So we're kind of expanding this tree of different possibilities here, and we can see there's no point in carrying on down this branch of the tree. Okay. So we might try this one next and look at the vertex in the top right. And again, we might try red, yellow, and blue. And now, neither this branch nor this branch are any good because this one violates the constraint these 2 should be different colours. This one violates the constraint that these 2 should be different colours. So, only this branch is any good. So, continuing down this branch, we finally try assigning something to the top left, and again we've got red, yellow, and blue, and we can see that only one of these is a good colouring, which is this one in the middle. Okay, so what we've seen is the algorithm's explored this tree of possible solutions, but it's not explored very much of the whole tree. Like if we were exploring everything, completely blindly, we'd have kind of gone off down here somewhere on the bottom left. But instead, we've only kind of honed in on the solution much more quickly than exploring everything. Okay, and this approach, which you might call trial and error, is often called backtracking. And the reason is that you explore some parts of the tree, and if you find something that doesn't work, you go back up the tree, so you backtrack further up. Okay, so this general approach of backtracking can be used whenever we can check whether a partial solution is correct, so whether it can be extended to a full solution or not. Okay, and what we have is a quantum algorithm for accelerating any algorithm based on this approach, roughly speaking. I mean, there's some caveats which which you can ask about if you'd like to learn more, but just to summarise what the result is, if we have a backtracking algorithm like this, with t vertices in the tree that it explores of all these possible solutions, then there's a quantum algorithm which runs in time about square root of t, up to some kind of lower order terms, and it finds a solution to the constraint satisfaction problem, or says there's no solution if that's the case. So it achieves about a square root speed up over the classical algorithm. Okay. So if we think of t as being very big, this root t versus t as the main parameters, this gives us a square root separation. All right. So this is an example of some such square root speed up. And many classical algorithms which are actually efficient in practice turn out to be based on this approach. For example, if you have the Boolean satisfiability problem, or SAT, which is a famous NP-complete problem, and you download a SAT solver from the internet, it will probably be based around backtracking. And these are things that are really surprisingly efficient for problems you see in practice. And there are some other applications that we know of this algorithm now. For example, people have proposed to use it for attacking lattice-based crypto systems because the classical algorithms for this are based on backtracking, so we might be able to apply the quantum algorithm and get a square root speed up. And also recently, Dominic Moylet and Lyndon and myself showed that we can use this algorithm to accelerate a classical algorithm for the travelling salesman problem, or TSP. So people over the years have developed many interesting classical algorithms for this problem, which are better than the kind of naive approach that you would have. The travelling salesman problem is about visiting every city in the shortest time, and rather than trying every different possible path one after the other, it turns out there are much more clever things you can do. And one of these clever classical algorithms is amenable to this backtracking speed up approach. So we get an improvement there in the classical runtime. And I expect there'll probably be quite a number of other applications out there. Okay, so in the last few minutes I want to mention a totally different algorithm. But first I want to highlight something which is not a result of mine, but I think it's something which is maybe not that well known, so it's worth mentioning, which is as one of the most sort of general purpose things one could imagine that one would try and do with a quantum computer, which is add a bunch of numbers together. So it's maybe slightly surprising that this basic task in arithmetic can be sped up with a quantum computer, in some sense at least. Imagine we've got some n numbers, x1 through xn, and we want to compute the mean of those numbers, 1 over n of sum over I of xi, up to accuracy epsilon. So we want to approximately compute the mean of these things. And we imagine that n is very big, so we don't really want the runtime of this to scale with n. We want it to scale with the accuracy, but not with n very much. And it turns out that there's a quantum algorithm for this problem that achieves a square root speed up over the best possible classical algorithm. So the best classical algorithm must take time order 1 over epsilon squared, but there is a quantum algorithm that runs in time order 1 over epsilon. So this is an extremely simple problem, but it's kind of remarkable that we can get a quantum speed up even for this. And you know, this sort of approach of approximating the mean of some sequence of numbers, you know, the natural way you do it is sample some numbers from the sequence and take the average. And this kind of randomized approach can be seen as a really simple example of a so-called Monte Carlo method. Okay, so what's the Monte Carlo method? Monte Carlo methods are designed to use randomness in order to compute some property of a system which is too large or complicated to work out deterministically. So, for example, we might have a complicated system like the weather, where we want to find, I'm not sure if you can really see this, but this is supposed to be a typhoon, I guess. But you might have some weather system where you want to work out what the temperature is like to be on a given day, but you know, it's very hard, like, because of you know, small changes in the initial conditions. It's you know, if you just start out with today and kind of evolve the equations for the weather, you know, forwards, and then work out what the temperature will be, you know, in a month's time, probably it's quite inaccurate. But so what you might do is try many different possible, slightly different initial conditions and evolve these all forward and take the average of the temperature after a month and say that that's your guess for what the temperature will be in a month's time. So that's one example. There's the weather. You might also think about the value of some financial products or any other kind of thing which is kind of complicated to understand, but which we can run it forward in time and, you know, take the average of the outcome to find out, you know, what its property is like to be. So, I mean, the basic core of many of these methods is to approximate the average output value of an algorithm A to within accuracy epsilon. Okay? Because we imagine we have some randomized algorithm, we want to approximate its average output. And we often assume we know a bound on the variance of this random variable given the output. And say the variance is at most sigma squared. Classically, you know, we do this by just taking the average of some number of runs of the algorithm to, and you know, what we need is order sigma squared over epsilon squared, it turns out. That's the number of runs we need to achieve accuracy epsilon. And quantumly, we can do better. We can achieve order sigma over epsilon, roughly speaking. There's some lower order terms here which are hidden by this O tilde notation here, but it's roughly sigma over epsilon. So the classical complexity was the variance divided by epsilon squared. The quantum complexity is the square root of that. So this is pretty good if the accuracy you want is very high, like 10 to the minus 6 or so. So another interesting thing is that the underlying algorithm whose average, you know, output value you're approximating can now be a quantum algorithm itself. So this might enable you to get a quantum speed up from that part of the algorithm as well. Okay, so this is everything I wanted to say today. So basically I just wanted to show you very briefly that quantum computers can speed up two of the most basic tasks we might try to solve in classical algorithms. Firstly, we can solve this. We can speed up this approach called backtracking, which is one of the most practically useful ways of solving constraint satisfaction problems. We can also speed up these Monte Carlo methods for approximating the mean of some random variable that has bounded variables. And I think there's probably, you know, other nice general purpose quantum algorithms that we could discover, many of which could be quite useful for, you know, really practically relevant problems. So that's everything I wanted to say this morning, so thanks very much.
Thank you, Ashley, for you're off by 10 seconds.
10 seconds. No, I was too early.
Yeah. Okay. Questions for Ashley? We've got microphones there, so that makes you feel more confident. I can start. You invited a question in terms of the caveats behind the result of the backtracking algorithm. Can you say what you think this dog is going to?
Sure. Let's go back to this. Okay. So. Right, so the first thing to say is that this algorithm allows you to speed up classical algorithms that are sort of vanilla backtracking algorithms, if you like. That they have this property that they explore this tree kind of in a fairly sort of naive way, if you like. The classical algorithm goes through all of the possible leaves and branches of the tree, and it only uses at any point kind of local information about where it is. Like, if you're down here in the tree and you're looking at how you're colouring this vertex in the top left, you don't use some information you might have gained from over here in the tree, or something like this. So the quantum algorithm, because it explores the tree in superposition, it can't use any information that's previously gained from elsewhere in your attempt to solve the problem. So it can't speed up more complicated algorithms, like in particular branch and bound algorithms, which approach people use for solving optimization problems. We don't know how to speed up these yet. And also, the runtimes in terms of this number of vertices in the whole tree, and if the classical algorithm might not explore the entire tree. Like maybe it stops when it finds a solution, and maybe the solution is found very, very early on. So then, in that case, the quantum runtime might not be the square root of the classical runtime. It might be a bit worse. So.
Yeah.
Could you say something, how do you go about actually, could you say something about how you actually make a new quantum algorithm? What's the process?
Right, so very, very good question. I wish I knew. I wish there was a process. So I think, in some ways, it's very similar to how you would design a new classical algorithm, right? I mean, you first go through your toolbox and see if some other algorithm already does the job, or maybe, for example, really what you want to solve is unstructured search, and you can just apply Grover, so it's fine. And then you see if there's some kind of simple modification of the algorithm which will, this known algorithm which will achieve that, and the answer may be no. And then you sort of see if there's, I guess, this is probably now then a good point to go to the other side and say, well, is there a reason why we can't come up with such an algorithm, like some known lower bound or something like this? Then, if not, you have to start thinking quite hard. In the case, just to say, the case of the Monte Carlo one that I mentioned later on, it was known that there was an algorithm, which I think I mentioned, for computing the mean of a random variable where the values are bounded. So then, the question is, can you extend this to one where you have a bound on the variance, not the maximum value taken by the random variable? And then you just start trying to use the tricks that you know from algorithm design to try and speed this up. What is very, very difficult, of course, is coming up with a quantum algorithm based on totally new techniques. And there, I think you maybe have to be Peter Shaw, or you have to have a very good idea in order to do this. Yeah.
Time for one more question. Yes.
Actually, are there opportunities for super polynomial speed up for some of the optimization, maybe special aspect parts of the constraint satisfaction problem area?
Well, it's a very good question. At present, it's fair to say that we don't really know, because often we can't prove lower bounds on the runtime of even classical algorithms, let alone quantum algorithms. So, all we somehow have is the intuition that we've got from years of work on quantum algorithms. And the intuition so far says that if you have some quite general optimization problem to solve, then the chances are that in the worst case you won't get more than a polynomial speed up over the classical algorithm. But on the other hand, this doesn't mean that there aren't instances for which you might see an exponential speed up. And then the interesting question is, are these instances the ones that you care about in practice, or are they not? And you might be able to say, well, a given classical algorithm we can get an exponential speed up, but then maybe that's not the right algorithm to use for that particular problem. So it's a real challenge. The adiabatic algorithm, which people care about a lot and has been around for 15 plus years, we still don't have a good understanding of whether we are likely to see an exponential speed up for quantum algorithm as an approach for solving optimization problems. And and it's just very difficult challenge.
Okay, if there's any other questions, I think you could probably approach Ashley at lunch or something.